Thank you, Rob, very much for this very nice introduction. The hobbies I execute absolutely in that order of sequence, as you have mentioned that. All joking aside, thank you very much for attending this presentation today. Let me spend a few words on aixergee before I get to the content of my presentation today. Some of you, I hope many of you, know aixergee as a service provider for the cement industry, and we are probably most recognized for our CFD modeling and our CFD consultancy services. And that's not wrong, but it doesn't tell the whole story and it doesn't reflect our motivation. Our motivation is captured by the term in our logo, which is process optimization. Our main target is to optimize processes, and so that's why we are working at the very root of what this conference is all about, the optimization of production processes in the cement industry. And what we carry to the market is know-how, is knowledge about the physical and chemical processes being involved in the production of cement in all its various steps, from raw material grinding over clinkerization down to cement production in the mills. We focus on the physical and the very chemical basics of the processes involved. And then we cast this knowledge into models. These models can be of various types. They can be CFD, they can be process, they can be all kinds of things, and I will show you in my presentation what this means for you. But we've been listening to the buzzword this morning already many times. What is driving us these days is Industry 4.0, Internet of Things, machine learning, all these buzzwords. And we will be sitting here, and Klaus Beck put it very right when he made a statement just before the break. We have to interpret what does it mean for us. Industry 4.0, everybody's talking about it, but we as a cement industry, we have to interpret what does this mean for us. And in that sense, I am happy to present to you today a new tool which we have added to our toolbox that gives us the position to optimize calciners and preheaters and other cement production equipment with data and model-driven optimization. Also, Marie has pointed out that in her presentation today, we are getting together all kinds of information on the production process to learn more about it and then to optimize it. And model-driven optimization and data-driven optimization are two different animals. Data-driven means you take the real data and try to analyze what is going on, whereas in model-driven optimization, you set up a parallel world, a virtual reality, and then you compute forward how this process would behave. And now we are in the position to marry those two together to the mutual benefit and transfer information from one world to the other and steadily increase our process understanding. So let me start off with putting a very funny question maybe, or unexpected question. What do process engineers and archaeologists have in common? I don't know whether we have archaeologists in the auditorium. We have one specialist in geoscience, I know. So maybe Rob can add something to this discussion.
Is it the love of beer?
Is the love of beer and another thing I'm going to talk about. So you might feel this question to be strange, but I'm going to show you there is actually a lot they have in common. First of all, they both have to understand the whole picture, like, for example, why did the dinosaurs get extinct? But they have to justify and argue that on the basis of small piece evidence. If a process engineer is put the question, why is the kiln capacity limited? Why don't we get more out of our kiln? He will be digging for information from the data system of the plant to try and find an explanation why the kiln is getting unstable and the production is limited. So it's sometimes like looking for the needle in the haystack. And the archaeologist has the same problem. The usual thing we do as process engineers, we spend probably 50% of our time digging data in the process control system and trying to find an explanation. Every time we think we have found an explanation why the kiln got weak, then somebody else looks over the data and finds a counter argument and says, no, this is not because of that, it's because of that. So that's how we spend our time, and I think many of you know what I'm talking about. It can be very complicated to try to understand and read the data. So the challenge is where to dig. If you are an archaeologist and you want to try to solve the question why did the dinosaurs got extinct, you will be probably looking for a skeleton or a bone in order to analyze this bone. But the first question is, where do you dig? So, where to dig and what is the right tool to find it? Next question is how to dig. And I ask you to transfer this always to our process engineering. If I'm talking about digging, where to dig in the massive data we're having. How to dig. Better to dig in a big area, but only on the surface, or to drill a very small but deep hole. To put it into perspective as a process engineer, if you are looking for the reason of the swinging calciner temperatures, you can evaluate all the data from the complete plant, but only in half or middle average values, or you go only for the 10 data related to the calciner, but then you analyze them for every millisecond. And you will get different results from it. Next thing is how to stay focused. You will be getting lots of data, and I personally know some people in the auditorium which we had projects together, and we spent days and weeks looking into data, analyzing the data, and we got confused. We analyzed data till our eyes rolled, and we didn't know where it's left and right and up and down. And I think you have the same experience. So the work sequence can be, on an abstracted level, be summarized to go according to this sequence. It's always the same. First, you'll have to get an orientation. The question is, where should I try to find evidence? Where should I dig? Next, you will be keen to confirm what you found out to be the right orientation for you. Then you would be searching for evidence. Then you would be proving your evidence. And that finally leads to understanding. And that is the point where you want to go. You want to understand what's going on. Only then you can improve. So this is the generalized sequence of work which applies for a process engineer as well as an archaeologist and many other professions as well, but I choose this comparison. And I'd like to take you now along the workflow, along this workflow, for a process engineer and an archaeologist, and tell you and visualize what challenges, what questions will be put. Let's assume, for example, there's an archaeologist who has set up the hypothesis that the dinosaurs got extinct in England because of malnutrition. I don't know why I come to this picture, I don't know, but we'll see. And a process engineer is trying to answer the question why the kiln production capacity is limited. So let's start with the first phase, orientation. The archaeologist would have to first answer the question where to build my camp. Where do I go? Do I go to Chile, to London, or Staffordshire? I don't know. He will be using maybe airplane or satellite explorations to find information on the soil, which gives him indication this is the right area. The process engineer has the same challenge. He would be asking himself, which are the operation parameters which influence my problem? And there are thousands. The usual way to do it is data analysis. This is where we spend our time with. We take trend data from the PCS and then we analyze until our eyes get rolling. And this is the new thing I want to present to you today. We have developed algorithms and tools which help to analyze these data in a certain way. I will give you more details later on. Next step, you'd like to confirm that you are digging at the right position. So the question for the archaeologist would be, was my airplane exploration correct? And he will do some test diggings at that ground. The process engineer will have the question, did I identify the right parameters, or am I in the wrong position, in the wrong area of the cement plant? We can do that by applying dynamic flowsheet modeling. I will tell you the details later on. Those are tools which we would apply, which we have at hand in our toolbox, which we can apply to such projects. The next is the search of evidence. The archaeologist would put the question, where's this dinosaur bone? I want to have a skeleton, I want to have a bone because I want to analyze it for nutrients and all this kind of stuff. He will be taking information from this bone, and he will have to hand scrape meticulously, which means he has to get down to his knees and millimeter by millimeter scrape away the surface until he finds evidence. On this detailed level, we would be using CFD, very detailed, rigid, physically driven, chemically driven, first principle modeling. For example, if we might have the suspicion that there's a meal box which is not working correctly, and maybe this meal box doesn't suspend the meal correctly. This is one detail out of 10 million possibilities in a cement plant. And if you look at the data set from above, it's not so easy to arrive to the interpretation that is just this meal box that's not working. So then it's also important to prove your evidence. I mean, you can find something, but then you still have to show that this is actually the one that is causing the damage. So the archaeologist might have found this bone, and he will run it through a C14 analysis, for example, to define the age of this bone, to say, well, this can really be a dinosaur bone, or maybe it's a pig bone that just happened to come to the same place later on. So you have to prove your evidence. And the process engineer would have to ask himself the question, would the process be improved if I change this splash box? Because if it doesn't change, then obviously the splash box isn't the root cause for this problem. And for that reason, he would apply a simulation of an improved design and would again use it in a very detailed CFD to prove that a change of design would actually change the whole process. And finally, the stage where we have to go to is the understanding, which requires taking these results and discuss it and get it into the bigger picture. Like, for example, the archaeologist would sit down with other experts and say, okay, how could I discuss, how could I testify the malnutrition in that bone I found, or maybe there are other reasons why dinosaurs got extinct. And the process engineer would take it to the next level and would try to derive from his finding a general rule of how to design splash boxes. And he would also have to check whether there is such thing at all, a general best design, or isn't it more the case that one design would be good for this application and another design would be good for another application. So this is the level of understanding, and that's where we want to go. And now I'd like to walk you through this step in more details for the process engineer and show you what the tools are which we can use. So we're starting again with the same objective. Our kiln production is restricted. We see fluctuation in the kiln operation, and we have to overrun the main burner in order to make sure we're producing quality. It's a well-known problem everybody, or many people have in their cement plants, and we're trying to find out the root cause for it. The archaeologist is excavating a wide area. In semi-process engineers talk, we're looking at the data set of the complete plant. We've been told in the previous presentations, especially the one from Fabio in the morning, that, for example, Votorantim, but also other suppliers are actively pursuing this digitalization agenda, so they will be looking at the complexity of their data and trying to find out how can I extract information from it. Same thing we are doing here. So we would say, I'm sure the reason for my process limitation is somewhere here, but where is it? Where in the hell is it? Our natural response as process engineers would be to say, if I have a weak rotary kiln, probably it's in the rotary kiln. But if we dig deeper and deeper and deeper, and I look into your eyes, I know you're saying it's right what I'm saying. You walk along the logical chain and you develop your interpretation and your analysis. You will end up in the calciner preheater tower. The next thing you might say, okay, the dosing is not correct. Then you might say, okay, the pneumatic transport from the silo is not correct. And then you say, okay, there are layers in the silo. And you would say, oh, the raw mill is not working consistently. And finally, you end up in the quarry and say the quarry is heterogeneous, and we didn't take care about homogeneity in the quarry. So it's very easy, and it's not to be underestimated. It's very easy to have a problem here, to experience a problem here, and end up with the root cause being here. Or being here, or there are many places. Talking about alternative fuels, it's a nightmare. And previously we have been discussing, you have been asked, Mary, wouldn't it be just better to have a stable running process with stable feed materials? Yes, that would be nice, huh? No chance. Reality is completely different. So this is potentially all those areas can contain the root cause for our problem. So how to do it? We usually then sit down and evaluate trends. We have 10,000 signals. Some of them in seconds, some of them half-hour values, whatever. We have 10,000 signals. We sit down, pull up trends, and then we analyze these trends and we develop hypotheses, sometimes stranger than universe. The problem is, we automatically connect our knowledge to it. So the trends we put on here, we put them on because we believe they have an influence, but we don't know. And we cannot put 10,000s on it. We can only put 6 or 10 on it, then we lose control. So this is the way we do it, but it's not necessarily the best way to do it. What we propose here, and this is what we've developed new, is algorithms that help us doing so. So we take a comprehensive data set from the process control system, and we have algorithms in place that analyze them without influence of process knowledge. It's the maximum stupid machine, and it's just trying to find out coherent, coincidental data sets. So the metrics that is produced by this algorithm can be seen here. It's of course not well visible, but these are the data, the signals set against each other. So like for example, you would have preheater cyclone exit temperature 2 and preheater cyclone exit temperature 3. Do they correlate? Which means correlate. They go with the same movement or with a counter movement. Do they go in the same frequency or a different frequency? There are certain characteristics which are ready to be analyzed on, and what the system does, it displays a big dot if there's a big coincidence, and a small dot if there is no coincidence. And it displays a blue dot if it's a positive coincidence, and it displays a red dot if it's a negative coincidence. So what you then do, you take those spots those areas where there are big spots, because the functional relationship can either express in a coherent or in an anti-coherent way. So this gives you hints where you should look at. This is like an airplane survey for an archaeologist. So this tells us, oh, we have to look here, we have to look here, we have to look here. And all this, of course, relates to measurements, and they relate to process equipment. So now we have narrowed in our territory, and we might have found out that we have to keep on looking for the root cause in this area. We now use dynamic flowsheet modeling. We insert our knowledge into dynamic flowsheet modeling. The identified parameters and the models are put in place. It's like an Excel tool, but it's more elaborate because it also can use counterflow processes and provides a lot of advantages to use this tool instead of just trying it at the plant. You could also go and try it at the plant, but you run the risk of damaging something and you don't get everything, all the other parameters stable at the same time. With this dynamic flowsheet tool, you keep everything alike, you change one parameter and you see the reaction of the process. And this is an example of such thing. This is a very strange calciner which we have set up in a dynamic process model flowsheet. You see those red boxes here. These are basic process units like mixing, heat transfer, separation, and all these kind of stuff. So we model the process on both process units. And what you see here, for example, is a diagram that calculates the degree of calcination of the hot meal depending on how the meal coming from here is taken upwards or taken downwards. And it's very important. If meal doesn't go down, it doesn't reach here. If it all goes upwards, nothing happens here. So this is influencing your process stability. So we now have then found out that we have to look at in a detailed level what's happening here. I'm sure it will be here. So next step, we do CFD. And we do rigid physical CFD. What you see here is the same calciner in CFD. And you see it is being fed with 3 different meal streams here and one fourth meal stream here. And we can identify and track every particle and evaluate where are you going, what time have you been sitting at that temperature, what is your calcination degree, where are you going, you're going up or you're going down. So due to the shortness of time I have to hurry up a little bit, but you can surely assess what quality of information we're getting here. And we're taking it even further by not only evaluating it optically, we can evaluate every single meal particle and look after what time, what is your fraction of particles going upwards or going downwards. And related to that, all the chemical data like calcination degree and all this. We can do the same for fuel. We can ask the fuel particles, what is your burnout degree at every time and in every position. Now, having done all the detail, we can backwards transfer this process understanding into the process level modeling. So we will be able to dynamically calculate what's happening in this calciner on a very precise level with very precise knowledge. And the big advantage now is we can do predictions. We can now use this model to make predictions. For example, change the type of the splash box to stay in the picture and see how the process reacts. So we found out that from the big area, it is important, in this case, to look in detail at the calciner. And this all is summarized into what we call comprehensive model simulation. And let me just explain you briefly what you see on this slide. You see in the center again this process flow sheet, but on the left-hand side we have now specifically looked into the splash plate. And you see 2 different types of splash plates here. One meal boxes, I have to say. One meal box without splash plate and one with a splash plate. And it's a tiny little difference. It's a horizontal table of 200 millimeter length that makes a difference in the splashing efficiency of the meal. If you look here without the splash plate, you will have occasional drop down of meal, which you don't have here. And this makes a difference, and this in reality is the root cause for many kilns suffering from heterogeneous pre-calcination, which makes the kiln operator run the main burner harder and thus producing more exit gas and thus throttling the ID fan and thus limiting your production. In many cases it's a small thing. You don't always need to have a new calciner, You need to know exactly where is the root cause for your problem. I'm coming to the end. Data and model-driven optimization can work together mutually and provide benefits. You can exchange information from one world to the other and make use of it. But process optimization in general requires knowledge. Knowledge sometimes hides behind complexity. I think we know all that. There are two principal ways of knowledge acquisition. Data analysis, which is basically a deduction from reality, and model understanding, which is basically the simulation of reality. And then you can marry those two worlds together, can be combined. The keywords here are artificial intelligence, model-based interpretation, machine learning, all those buzzwords you know already. Important is you'll have to apply your scrutiny to different level of detail and to different width of application. You have to play with it. You have to exchange those things from one world to the other. There's the plant level, which we would answer with a process level model. There's the meso or department reduced data field, which we go dynamic process modeling or CFD, and then there's detail up to every molecule. If you go for emissions, for example, NOx or something like that, we go for every molecule. Introduction of data mining technology is now available, closes the gap between modeling and real data evaluation. And we are in the possession of all these tools and can combine them. And we have actually used all those tools, although not together in one project, and we will only use those models which are actually necessary and especially commercially, cost-wise necessary. Thank you very much for your attention, and for those of you who have never been able to step inside a running calciner during operation, we have a goodie for you in our booth over there. We have our real physics virtual reality 3D goggles. You can walk inside a calciner and see how the wheel behaves, how the fuel goes and how it burns, how the temperatures are. But you will be safe. So we will be very happy to see you there. Thank you very much.
Thank you very much indeed, Matthias, for a very interesting insight into what can be done to model processes in the cement plant. Just before I get on to the questions, the specific questions, did I understand that actually you set up a model flow sheet, you use the predictions from that to inform your CFD modeling, and then the results from the CFD modeling are then put back into the model flow sheet? Okay, so I'm not wrong there. But does that not extend your connection to the original data by too far?
Could be possible, but the thing to understand is here, whether we talk about process model, flow sheet model, or CFD model, those are platforms only. And what is important is to transfer the knowledge you gain from the one world to the other world, and you can give it back to the other world again. So we're talking about width and depth, and CFD is always very deep, and of course CFD cannot be wide. So process is always a little bit wider, and on top of that we have this data mining. So it's a matter of combining wide and deep technologies.
Okay, we have some very specific questions here. One of them is from Paul Flashkamp. How long does a typical project of yours take and what needs to be invested? And Mark asks, where does the information come from to build the model?
Very many questions. A typical project runs for about 3 months. Complex projects can go over a year. The cost will be, if we use these technologies, the cost will be north of 20,000 usually, and on top there is no limit because it depends on how many iterations, how many runs, how many models we have to build. Where do we get the information? Like for example in the data mining example I showed, we will be sitting down with the client and tell him what kind of data we need. And in this case, things can be very easy because we actually take all of them. Because it's a machine algorithm, we don't have to compute it ourselves. For the CFD, I think what this question relates to is a very critical point, and we had that also, rubbish in, rubbish out. The CFD model is nothing else but giving physics and chemistry space to act in, which means we only define the physical and chemical rules, and then we push the button. And what comes out as a result, we don't know up front. Which means if we put the wrong boundary condition, as we say, if we put the wrong start position, then the result will not be representative. So we have to take extra care, and we do that, and there are ways to do it, to start with the right boundary conditions.
Okay, so for example, how do you ascertain the exact physical dimensions of the process containers, if you like?
Yeah. The right geometry is one of the traps you could fall in. We need absolutely the right geometry. If the client has a 3D model, would be best. Otherwise, laser scans help. Otherwise, we will set up a geometry and give it to the client for clearance, which we do generally with all boundary conditions. Before we let the computation run, we always have a clearing with the client. The same thing goes for the boundary conditions. We do conventional heat balance checks to find out whether the data is consistent. Like for example, if the client says we have tertiary air temperature of 900 degrees and we have this and that fuel split, we have this and that fuels, we have this and that production, our ID fan is running at this and that RPM, and we put all that into a conventional mass and process flow sheet calculation, and we detect where the data are inconsistent, and then we get back to the client and clarify that.
Okay, so two very brief questions. Does your tool, this is from Felix Barknecht again, does your tool analyze only steady state or also variable process conditions, considering that a plant often needs 30 days to stabilize? A brief answer.
Yes, of course. The big thing about CFD is it's not steady state. If you remember the pictures, the particles are flowing. It's not steady state. It's dynamic.
Okay, but the maximum extent of that particular analysis was 20 seconds.
Yes.
So could you run that forward by 1 hour and see whether or not things have stabilized after 1 hour?
Good question. From the data analysis, we see the type of correlation. And if the correlation says there is a cycle coming up, running for 20 minutes, for example, we can also, of course, run the simulation for 20 minutes. But then stay economical, we would have to reduce the level of detail only to that parameter which we are chasing, in order to have a simulation over 20 real-time minutes run to a cost that can still be borne.
Okay, and so the final question was, did they put in the splash plate, the new splash plate? Yes. What was the result?
Yes. The splash plate thing is an archetypal problem, and we have solved, I think, at least 10 or 20 problems in cement plants by introducing small scale like splash plate or brick lining splash geometries, and help tremendously.
Okay, that's all the time we have for questions. But once again, let's join together and thank Matthias Mersmann for his excellent presentation.